We're going to have a slight tech delay as we get your laptop plugged in. Can I ask you to plug your laptop in first, just to make sure that works? We're doing a microphone check right now. Please talk to me.
Hello?
Are we getting anything in the back? Great. Our next speaker of the session will be Longfei, talking to us about verifying termination in Byzantine protocols. Take it away, Longfei.
Okay, so I'm Longfei Qiu from Yale University, and I'm going to present our result on formal verification of asynchronous Byzantine consensus protocols. So let's begin from a review of the concept of consensus protocols. It's one of the central problems in distributed computing. And the goal is to achieve safety and liveness while tolerating a subset of Byzantine faults. And any distributed protocol needs to make some assumption on your communication model. And usually in the literature, we have three kinds of communication model. Synchronous model just means your messages are always delivered within a certain bound. But it's a very strong assumption in practice. So most protocols make a partial synchrony assumption, which means the network can be either synchronous or asynchronous. However, these protocols cannot tolerate, they cannot maintain liveness progress if you have an asynchronous network. And so we have a third class of protocols, which is asynchronous consensus protocols. These protocols do not need to make any assumption on network latency as long as it's eventually delivered. Now, if we look at the literature on these classes of consensus protocols, we see that for partial synchrony protocols, it's considered easy to implement, and its correctness is by now probably very well understood. And we have a very long list of works verifying the correctness of these protocols. But if you look at asynchronous protocols, we see a very different picture. They are considered very notoriously hard to understand, difficult to implement, and we have very few results verifying their correctness. So why is asynchronous consensus considered much harder? Well, first, there is a well-known theorem called the FLP impossibility theorem, which basically says you don't have deterministic liveness or in the asynchrony world. And so every asynchronous protocol needs to make some probabilistic decisions in order to make progress. And probabilistic programs, especially probabilistic distributed algorithms, are very hard to implement because you can have a very subtle bugs. And also here, you don't have your deterministic liveness guarantee. What we actually have is probabilistic liveness. Your command will be executed with a probability that converges to 1 over time. And we call this almost sure termination. And the other factor is that if you look at the design of these protocols, you see they have much greater structural complexity. If you look at the protocols like Raft or even Ji-Yong, these partial synchronous protocols, they are easy to describe. But with asynchronous protocols, you usually have a large bunch of cryptographic components. And in fact, there is a well-known bug concerning a protocol called the Honey Badger BFT protocol. It's an asynchronous protocol that relies on a cryptographic component called the common coin. And soon after it's published, it was found that it contains a very subtle liveness bug. So in this work, we especially study the problem of formal verification of these asynchronous consensus protocols. We introduced SureDistrib, which is a framework formalized in ROC for defining probabilistic I/O automata, and we support a parallel and layered composition of these automata. And we use this to formally model asynchronous consensus protocols, and we show how to prove probabilistic liveness of these difficult protocols. And concretely, we deliver the following result. We give you a formally verified asynchronous binary agreement protocol that's implemented as a from a modification of the honey badger protocol, which is known to be buggy. So I'll first give an introduction to the features of SureDistrib. Then I will introduce the approach we use to prove almost sure termination of our particular protocol. So in SureDistrib, we represent probabilistic I/O automata as transition systems over distributions of states. And we represent each distribution as a list of a state and a probability value pair. And we allow two kinds of transitions, small step transitions on these systems. We call them split and action steps. In a split step, you select a particular state element in your distribution, and then you split it into multiple elements with the total probability summing to the original probability, but you don't change your state. This is usually a probabilistic stuttering step. And the action step is the place where the actual state transitions occur. And this can also be probabilistic. And since this is I/O automata, we further divide the action steps into three kinds of steps, which we call opponent steps, proponent steps, and the local steps. The opponent steps is basically you receive some invocation from upper layer application. And the proponent step is you return some information to the application. And all other steps which are invisible to the upper layer is called local steps. And we simply model everything that's about the Byzantine processes as local steps. And in this work, we assume that the automata state is completely transparent to the adversary. So any I/O about the Byzantine state processes can be modeled as local steps. And as said, we support two kinds of composition, which is parallel composition and layered composition. In parallel composition, you let the automata execute in parallel, whereas in layered composition, you define overlay applications of your automata. So here's how layered composition looks like. You have your underlay automata, and then you can define how honest processes interact with the underlay. And you can layer this to many layers. So with this, if we look at the proof architecture again, if you look at this figure horizontally, you will see these copies of the instances of a graded crusader agreement. And these represent individual rounds of the protocol. And that's a horizontal composition. Whereas if you look at this figure vertically, you will see that we are implementing GCA from common coin, and then binary agreement on top of an infinite number of rounds of GCA. And that's layered composition. To do liveness proof, you need one final ingredient, which is you need to work with infinite traces of these I/O automata. So we handle this challenge by segmenting an infinite trace into a sequence of asynchronous time steps. So you recall that in the asynchronous network model, even though you don't have an upper bound on message latency, you still assume that messages must be eventually delivered. And so you can define a time step as a period of time where all your messages sent before the time step are delivered by the end of the step. So this is what we do. We represent the execution as a tree structure like this. And then if you look at this horizontally, then every step represents a time step. And so you look at how a single state element splits probabilistically over a time step, which represents the process of delivering those messages. And then you take a snapshot of the tree at every time step, and you represent your liveness conditions as safety conditions over these time steps. So that's so far about the features of SureDistrib. In the following, I will give you a very quick introduction about how asynchronous agreement actually works. It relies on a cryptographic component called the common coin. It's a global random bit that's not revealed until a majority of processes agree to reveal it. How you obtain this common coin is a difficult problem in cryptography, but here we just assume it's an ideal black box. Now, it turns out if you have this common coin, then there's a very easy way to do binary agreement. Basically, you first collect a set of valid inputs, and then you flip the common coin to get a global random bit. And now you compare your input set with your global random bit and make a decision. And there's lots and lots of protocols designed roughly based on ideas similar to this one, but this is basically how Honey Badger works. Now, it turns out for this idea to work, you really need the the collection step, the first step of collecting these valid inputs to have a property called a binding. And if you don't satisfy this binding property, then there is a way for the adversary to rearrange the network message delivery so you never get liveness. And that's exactly the liveness bug of Honey Badger. So what we did is that we implemented a modified version of Honey Badger binary agreement part that fixes the original liveness issue in our SureDistrib framework. And then we have to prove that this fixed version really satisfies the liveness property or the probabilistic almost sure termination. So here's the exciting part. How do you really prove that your protocol is probabilistically live? We give you a simple template for AST proof, which we call template hope, termination hope functions. Here's how it works. You define a state function on your transition system which satisfies the following three properties. First, it's always bounded between 0 and 1 and represents a probability value. Intuitively, it's a lower bound on the probability of termination starting from a particular state S. Now, you define two conditions, P and Q, such that if your Q is true, if your P is true, then your state function is always an indicator for Q. And also, this function has to be a sub-martingale, meaning over each probabilistic step, the expectation of this hope function should never decrease. And with these conditions, you can now invoke the optional stopping theorem. Basically, if you set your stopping time to be the time where P becomes true, then at that time, the expectation of your hope function becomes exactly the probability that Q is true. In slightly more detail, here's how you apply this template to asynchronous consensus protocols. We first fix n to be a constant, and then we let Q to be the property that either the protocol has terminated or all honest processes have completed the first n runs. You can then prove deterministically that this Q property will be eventually true. And this is usually very easy using the traditional tools of deterministic liveness verification. Now, you then set your P property to be the condition required for the protocol to terminate. And it turns out for Honey Badger, this P property is that at least 2 of the first n runs needs to reach a certain convergence property. Now, what we do is we define a hope function fns for every constant n. And we prove that this fns function is a hope function that satisfies the required properties on the previous page. And therefore, if you start from the initial state S0 and you complete the first n rounds of agreement, you can use OST to harvest the fact that your termination probability is at least fn S0. Finally, you take the limit as n goes to infinity, and you immediately get your almost sure termination result. We are, of course, aware that there's another line of thought on how to prove AST, which is using ranking supermartingales. But our experience has been that if you use the OST approach, then it's easier to derive quantitative liveness results. For example, we have a proof of the expected termination time. So to conclude, we introduced SureDistrib, and we gave a foundationally verified safety and probabilistic liveness proof of asynchronous binary agreement, and we are actively extending this approach to more complex protocols. Thank you.
We are back on time, so we have plenty of time for questions. Please step up to the microphone or raise your hand if you'd like me to run the microphone to you.
Thanks for the talk and nice work. I'm interested in this layered composition thing that you're talking about. Could you say more about how that operation, that automata operation works, the layered composition operation?
Yeah, so remember that we have your I/O automata has these 3 kinds of action steps called opponent, proponent, and the local step. Now, in layered composition, what happens is that you specify how these honest processes work by making these calls and returns. So you specify that under some condition, this honest process can make an invocation on your underlay, And that would be an opponent move from the perspective of the underlay. And then this underlay, under some condition, it can return some information to the honest process. And that's a proponent move. And then layered composition is basically defining a composed transition system that puts together all these transitions.
I see. So the proponent moves are the arrows, the downward or the upward arrows here?
Opponent is going down, and the proponent is going up. And these names come from game-based semantics.
Got it. Thank you.
Yeah.
I know the common coin is a black box for you, but are you sure that your common coin can be implemented?
Yeah, I can show you the formal definition, but we checked with the people in the cryptographic community, and it should be fine. Basically, you first, let me show you the paper definition. Yeah, so basically you have here, so you have a list of processes which called the open coin command. And then if this exceeds a certain threshold, the adversary can now call reveal coin. And then if you call reveal coin, then it randomly chooses a value from the given distribution. And that's our common coin. And we showed this to cryptographic people, and they think it's fine.
We're just going to start setting up the next talk, but we still have time for questions. Unfortunately, this means no more scrolling on PDFs for you.
Right. Very interesting. Thank you. I guess a couple of questions. First, if there is a bug in the protocol, what's the nice way to show actually that almost sure termination doesn't hold, or is there a nice way?
Sorry?
If the protocol is not correct, if you have a bug, what's a way to show that almost sure termination doesn't hold?
Well, if it doesn't work, then it's impossible to define the hope value function, because we have a formal theorem that if you have such a hope function, then it has to terminate with that probability as a lower bound. Concretely, I think there's a line of work from Nathalie Bertrand, and they are basically using parametric model checking to exhaustively explore the state space to see if to compute a lower bound for the termination probability. And if you read it, we can discuss more. It's offline, but there's some technical difficulty of their work, which our work handles.
Is there time for one more? No?
Let's thank the speaker one last time. Unfortunately, there's no time for follow-up.